Here we have some more complicated examples. It's a little bit harder to do them by sight, so you might want to slow down and do a substitution just to make sure that you don't make any mistakes and that you're actually doing it correctly. So in this problem, we have, this looks kind of messy. One thing I notice here is that the derivative of the square root of x, let's see, if you have the square root of x, that's x to the 1/2, the derivative of that is 1/2 x to the negative 1/2, or that would be 1 over 2 root x. Now I do have 1 over root x multiplying dx if I rearrange here, so I have 1 plus root x squared, and then I have 1 over root x dx, so that's pretty close. What I'm going to do is choose u to be 1 plus root x, and that way when I calculate the differential, the derivative of 1 is 0, and the derivative of the square root of x we just noticed was 1 over 2 root x, so the differential will be 1 over 2 root x dx, and I have a 1 over root x dx in the problem, so I could solve for 1 over root x dx. If I just multiplied both sides by 2, I'd get 2 du is the same thing as 1 over root x dx. Now that's enough for me to get this integral written in terms of just u, because we have 1 over u squared, and 1 over root x dx is 2 du. So we have basically 2u to the negative 2 du, just taking that 1 over u squared and writing it as u to the negative 2. I could pull out the constant. And now this is a simple power. When you integrate a power, the power increases by 1. So we're going to get 2 times 1 over negative 1 u to the negative 1 plus c, or that's negative 2 u to the negative 1 plus c. All we have to do now that we've got the integral done is substitute back in. So we have here negative 2 over u to the negative 1 would be 1 over u, and u is 1 plus root x, all plus c. Okay, so it's a little trickier. You might have recognized that from the very start, but if not, go ahead and make the substitution. You really need to know how to do it because it just saves so much time. Okay, looking at this one, I know the derivative of the arc sine is 1 over the square root of 1 minus the variable squared. So I notice I have the derivative of the arc sine. I've got here the integral. I've got 1 over the arc sine of y, and then I have the derivative of the arc sine multiplying dy with just a little rearranging here. So you think about that as dy over 1 and multiply those fractions, you'd be back here. So this means probably a good choice would be to set u to be the arc sine of y. That way du will be the derivative of the arc sine, and the derivative of the arc sine of y would be 1 over the square root of 1 minus y squared dy, so that I can write this as the antiderivative of 1 over u du, which we recognize as the natural log of the absolute value of u plus c, and now just substitute back. U was the arc sine of y, so we have the natural log of the arc sine of y plus c. If you go ahead and check by taking the derivative, you'll recover this function here. So this is the correct answer. Let's do a couple more. Ooh, this is a little bit tricky. But again, I've got that root t showing up in lots of places here. And the derivative of root t involves 1 over 2 root t. So I'm just going to try to clean it up. I'm going to let u be the square root of t. Then du would be, since this is t to the 1/2, the 1/2 will come down, I'll get t to the negative 1/2. That's 1 over 2 times the square root of t dt. I have here, if I rearrange slightly, I have cosine root t, and downstairs I have sine squared root t, and then I have a 1 over root t and a dt. So I actually have almost 1 over 2 root t dt. So one thing I could do would be to solve for 1 over root t dt by multiplying both sides by 2. So I find 1 over root t dt is actually 2 du. Now when I substitute in, I have the cosine of root t, but root t is u, over the sine squared of u, and then the 1 over root t dt is 2 du. If I pull that constant through, I've got the cosine of u over the sine of u times the sine of u, all du, which is 2 times cosine u over sine u is cotangent u, and 1 over sine u is cosecant u. And now I recognize what the antiderivative is. The derivative of the cosecant is the negative cosecant cotangent, so this should be negative 2 cosecant of u plus c. That way when you take the derivative, you'll get, you have the negative 2, but then the derivative of cosecant will be negative cosecant cotangent of u, so that will be the correct thing. Now just substitute back. There we go. Negative 2 cosecant of u, but u is root t plus c. You can always check your work by taking the derivative. We're good at derivatives by this point, so check and make sure it works out to be what you started with. Not always easy to choose the correct substitution. However, when I look at this one, I think to myself, might this have anything to do with an arcsecant? Kind of. Arcsecant would have 1 over the absolute value of x, square root of x squared minus 1. X to the fourth, though, is x squared squared. So if this is related to the arcsecant, a good choice might be let u be x squared. That way you have the square root of u squared minus 1, which is part of the derivative of arcsecant. If we do that, du would be 2x dx. I don't have an x dx in this problem, but I could make it if I multiplied top and bottom by x. If I multiply the top by x, I get an x dx upstairs, which I need. If I multiply the bottom by x, I get an x squared downstairs. So yeah, with that, let's see, now that I have an x dx, I can see from this that x dx is 1/2 du, since du is 2x dx. And I can rewrite everything. I think we have 1/2 du upstairs. X squared is u, and then x to the fourth would be u squared, so we have u squared minus 1. So this is 1/2 the antiderivative of du over u times the square root of u squared minus 1. And this one is the secant of the absolute value of u. So we have 1/2, oh sorry, not the secant, but the arcsecant. 1/2 the arcsecant of the absolute value of u plus c. Now just substitute back. U was x squared, the secant inverse of the absolute value of x squared plus c. Now, anytime you're taking an absolute value and you know the number is not going to be negative, you know the absolute value is not going to do anything, so you might as well save some time and reduce the complexity by removing those absolute value bars. Since x squared has to be 0 or more, and the absolute value doesn't mess with any number that's 0 or more, you might as well drop those. Okay, so we can see that substitution can be a pretty handy technique for dealing with some pretty crazy looking stuff. We sometimes have to be crafty. Think of it as solving a puzzle or finding your way through the maze. You might not always make the right choice for you to begin with, but don't give up. Keep trying different things. If you thrash around a little bit, a lot of times you end up finding a solution. And so that's the skill you want to cultivate. It's not necessarily knowing right off the bat what to do, but persisting. If you're careful with your substitution and follow those steps, choose the substitution, calculate the differential, get the integral rewritten so that it's clean, then do the antiderivative and substitute back, then you should be safe. A lot of times students forget this part, calculating the differential, and so watch out. Make sure that you do that. Once you make your substitution, the next thing you should do is calculate your differential.